All evidence suggests and all theoretical understanding of the formation of the moon indicate that it emerged from a collision with Earth. The moon has been a serene beacon in the night sky. However, recent observations suggest that it's undergoing a terrifying transformation. Seismic activities and mysterious changes in its surface hint at a potential disaster. Could these lunar shifts trigger catastrophic events on Earth? What chain reactions might we expect from our celestial neighbor? And most critically, how could these alter life as we know it? Come along as we delve into the terrifying transformation of the moon that could provoke a huge disaster on Earth. The Apollo 11 mission marked a monumental leap in space exploration, not only for landing the first humans on the moon, but also for bringing back invaluable samples of lunar rock and dust. When the astronauts returned to Earth, they carried approximately 1.6 kilograms of this material, which soon became the key to unlocking the mysteries of the moon's origin. Upon analyzing these samples, scientists discovered that the lunar rocks date back around 4.5 billion years. This finding was groundbreaking as it provided the first concrete evidence that the moon formed roughly 150 million years after the birth of our solar system. This era is now regarded as one of the most chaotic periods in our solar system's history. Astronomers believe that during this turbulent time, the inner solar system was teeming with around 20 small planets. These planets frequently collided with one another, and through these violent impacts, they eventually formed the 4 terrestrial planets we know today: Mercury, Venus, Earth, and Mars. One of these cataclysmic collisions is thought to have given birth to the moon. The moon's formation is linked to a colossal impact between Earth and a Mars-sized celestial body, which scientists have named Theia. This impact hypothesis suggests that when Theia collided with Earth, it shattered into countless fragments. These fragments, along with vaporized rocks and gases from Earth's mantle, began to merge over millions of years. These pieces coalesced into a disk that eventually formed a molten sphere. As the sphere cooled, it solidified into what we now recognize as the moon. For decades, this impact hypothesis has been the leading theory since it was first proposed in the mid-1970s. However, recent research presents a compelling twist to this long-standing narrative. New evidence suggests that the moon might not have formed gradually over millions of years. Instead, it could have emerged in a matter of hours. One critical aspect of the traditional hypothesis is the assumption that the moon is primarily composed of material from Theia. However, the analysis of lunar rocks challenges this notion. The chemical composition of these rocks closely resembles that of Earth's rocks rather than that of a foreign celestial body like Theia. Furthermore, the isotopic signatures found in lunar samples are strikingly similar to those found in terrestrial rocks, but markedly different from those found on Mars or other parts of the solar system. This evidence strongly indicates that much of the moon's material originated from Earth. Another intriguing piece of the puzzle is the alignment between Earth's spin and the moon's orbit. Both have similar orientations, a detail that further supports the idea that the moon is largely made up of material from Earth. This alignment is difficult to explain if the moon were primarily composed of Theia's remnants. These new findings have led some astronomers to propose that the moon's formation was not a slow and gradual process but rather a rapid event. One theory suggests that the impact between Earth and Theia was so intense that it caused a massive explosion, flinging material into space at tremendous speeds. This material could have coalesced into the moon in a very short time frame, possibly within hours. Such a scenario would explain why the moon and Earth share so many chemical and isotopic similarities. If the moon did form rapidly, it would reshape our understanding of planetary formation processes. This rapid formation theory could mean that other moons and planetary bodies in our solar system might have formed in similar ways, challenging many established ideas about how planets and moons develop over time. To explore alternative scenarios for the moon's formation following the colossal collision, researchers turned to a powerful computer program called SWIFT. This sophisticated software is designed to simulate the complex gravitational and hydrodynamic forces that come into play during and after such a monumental impact. The research team utilized a supercomputer affectionately nicknamed CASMA to run these intricate simulations. It's important to note that simulating these violent collisions is no simple task. The process requires continuous testing and refinement until the increased resolution of the simulations no longer alters the results. This level of detail is crucial for obtaining accurate and reliable data. Given the complexities involved, the team conducted hundreds of simulations of Earth-Theia collisions. They varied the angles, spins, and speeds of the impacting bodies in their models. Additionally, they simulated up to 100 million particles to represent the matter involved in these cataclysmic events. These high-resolution simulations provided a more detailed view of the impact dynamics than ever before. The results of these simulations were nothing short of remarkable. Contrary to the long-held belief that the moon took millions of years to form, the model suggested a much quicker process. Within just a few hours, the moon coalesced from the debris ejected from Earth and the shattered remains of Theia. This finding was groundbreaking as it challenged previous theories about the moon's formation timeline. Moreover, the simulations revealed that a significant portion of the material used to form the moon's outer layers originated from Earth. This insight provided a deeper understanding of the moon's composition and its relationship with our planet. The model showed that Earth's material played a crucial role in shaping the moon's structure, further emphasizing the interconnectedness of the two. To better understand the findings, researchers used the SWIFT program and the Coral supercomputer to simulate high-energy collisions between particles, exploring different scenarios and achieving unprecedented detail. These simulations showed that the moon could form within a few hours, challenging the previous belief that it took millions of years. The team varied the collision parameters, refining their models for accurate results. They discovered that much of the moon's material came from Earth, suggesting a close relationship between the two bodies. High-resolution simulations indicated that a rapidly forming moon could survive tidal forces and be pushed into a higher orbit. This new theory explained the moon's wide, tilted orbit, thin crust, and partially molten interior. However, to confirm this theory, scientists need to examine rock and dust samples from deep beneath the moon's surface, which remains a key objective of ongoing lunar research missions. These efforts will help verify the simulations and enhance our understanding of the moon's evolution and its interconnectedness with Earth. The simulations offer a clearer picture of the moon's evolution over billions of years, and accessing deep lunar samples is crucial for ongoing and future lunar missions to confirm these simulations and refine our understanding of the moon's formation. This research not only enhances knowledge of the moon's origins, but also sheds light on planetary formation and evolution in our solar system. Unlike Earth, which has been shaped and reshaped by various geological processes, the moon preserves ancient clues about the early solar system. The Apollo program, initially driven by Cold War rivalry, left a lasting scientific legacy by bringing back 382 kilograms of lunar rocks and soil. These samples provided insights into a massive collision between early Earth and a Mars-sized body, forming the moon and influencing Earth's evolution. The moon's surface, untouched by erosion or tectonic activity, serves as a pristine record of solar system history. Future lunar missions aim to explore unexplored regions and obtain deeper samples to uncover more about the moon's formation and evolution. Studying the moon is crucial for understanding Earth's history, and ongoing and future missions will help unravel the mysteries of our origins. The moon, located 384,000 kilometers from Earth, has deeply impacted human culture and science. Astrophysicist Neil deGrasse Tyson highlights potential threats posed by the moon. Despite its serene appearance, scientifically, lunar exploration via Apollo missions has advanced astronomy, physics, and planetary science, uncovering ancient volcanic activity and mapping geological features. Culturally, the moon inspires art, literature, and music, embodying exploration and mystery. Ongoing missions and studies continue to unravel its formation and composition mysteries, contrasting theories from lunar capture to giant impact hypotheses. An innovative hypothesis suggests an impactor struck a molten surface, forming a vast magma ocean early in the moon's history. The moon's anorthosite rocks and oxygen isotopes, akin to Earth, suggest a shared origin, challenging earlier beliefs about its dryness and formation. William Hartmann's 1974 theory proposed the moon formed from debris of a collision between Earth and a Mars-sized body named Theia, reshaping our understanding of lunar origins. The impact caused Earth to spin faster, and debris from both Theia and Earth was flung into orbit. This debris eventually coalesced to form the Moon. During this violent process, volatile compounds like water evaporated, leaving the Moon dry. The composition of the Moon, primarily derived from the mantle of both Earth and Theia, explains why it is less dense than Earth. While the Moon has a solid iron core like Earth, it is relatively small. From this tumultuous beginning, the Moon gradually cooled, and the molten surface solidified into a crust. However, the Moon continued to endure intense bombardment in the chaotic early solar system. The Moon's battered surface is evident in a global elevation map compiled by the Lunar Reconnaissance Orbiter, which shows the extensive impact over its history. The Apollo astronauts encountered rocks formed from widespread volcanic activity, a secondary effect of the numerous impacts. These rocks, shaped by ancient volcanic processes, tell a story of a once dynamic lunar environment. The craters and lava plains they explored provided clues about the Moon's volcanic past, revealing that it was not always the cold, desolate place it is today. Additionally, recent studies have shed light on the Moon's geophysical properties. Seismic data from the Apollo missions revealed that the Moon experiences moonquakes, some strong enough to cause significant shifts in the crust. These quakes are thought to be caused by tidal forces exerted by Earth's gravity, further highlighting the intricate gravitational relationship between our planet and its natural satellite. The Moon's lack of atmosphere also means that its surface is directly exposed to space weathering. Micrometeorite impacts and solar wind bombardment have gradually altered the lunar surface, creating a fine layer of dust known as regolith. This regolith is rich in tiny glass beads formed from the intense heat of micrometeorite impacts, providing a record of the Moon's history of space weathering. Volcanic eruptions on Earth are often fueled by water, which gets heated and pressurized due to the movement of massive tectonic plates. This water-driven mechanism is not present on the Moon. Instead, lunar volcanoes are linked to impacts that are forceful enough to melt the surface and release material from the hot interior. In the lower gravity of the Moon, volcanic eruptions would have taken on a different form. Molten rock would have splattered high above the lunar landscape, creating thin, smooth layers that extended far from the eruption source. These layers are what formed the mare regions, covering about 1/6 of the Moon's entire surface. Scientists believe these immense volcanic basins originated from large and violent impacts that occurred 3 to 4 billion years ago. The materials brought up by these impacts are composed of heavier compounds that would have initially sunk into the magma ocean. Modern technology, such as the LROC cameras, has helped scientists detect volcanic residues in recent impacts, providing valuable insights into the Moon's geological history. The Moon's volcanic history and influence on Earth reveal fascinating details about its geological and impact features. The Araras Plateau, with its lava-carved channel and volcanic glass deposits, and the Tycho crater, with its towering central peak and evidence of impact heat, are notable examples. The Moon's gravitational pull affects Earth's rotation and contributes to ocean currents, highlighting the interconnectedness of their histories. Water on the Moon is a complex topic. Initially thought to be dry due to the giant impact theory, recent findings suggest the presence of water ice, particularly in the Moon's polar regions. Studies indicate water may have arrived through comet impacts or been present in volcanic glassy globules. Discoveries by missions such as India's Chandrayaan, NASA's SOFIA, and China's Chang'e 5 have found evidence of water in lunar soil and rocks. Water ice is believed to be abundant in permanently shadowed craters at the Moon's south pole, potentially holding enough water to support future lunar bases. NASA's Lunar Reconnaissance Orbiter and upcoming missions like the Prime 1 aim to further investigate these icy reserves. Establishing a sustainable human presence on the Moon depends on local water supplies, crucial for long-term exploration and habitation. The narrative of Neil Armstrong's pioneering lunar landing in 1969 emphasizes the historic significance of human space exploration. Armstrong's journey from a passionate aviator to the first man on the Moon showcases his contributions to aerospace advancements and his enduring legacy. The Apollo 11 mission marked a historic moment on July 20, 1969, when Neil Armstrong and Buzz Aldrin landed on the lunar surface, famously uttering Armstrong's iconic words, "That's one small step for a man, one giant leap for mankind. During their approximately 2.5 hours on the moon, they conducted experiments, deployed scientific instruments, and left behind a plaque commemorating their visit. Their safe return to Earth on July 24, 1969, was celebrated worldwide, solidifying their status as heroes. Despite this acclaim, skepticism persisted, with theories suggesting the moon landing may have been staged, fueled by anomalies like the movement of the American flag and the appearance of the lunar environment in photographs and videos, challenging the authenticity of this monumental achievement. Their experience in the public narrative, the intense public attention and pressure to maintain a specific narrative could have contributed to their discomfort during the interview. This pressure, especially if they were concealing a significant secret, would increase stress levels, making it challenging to appear natural and at ease. There's also the fear of making mistakes in revealing the truth, which could explain their cautious and measured responses. This fear might have led to a lack of spontaneity and enthusiasm in their storytelling about the moon landing. Overall, interpreting the astronauts' body language and behavior is integral to the moon landing conspiracy theory. These nonverbal cues are seen as pieces of a larger puzzle, suggesting a sophisticated hoax where the astronauts, despite being honorable, were pressured to perpetuate a false narrative for pride or strategic reasons during the Cold War era.